Alright, hello. So today what I'm going to do is take this Echo Dot I had a teardown on earlier, and I'm actually going to look at the microphone kill function. So when you look at these devices, one of the things they advertise is that there's this button here, maybe the overhead view is a little easier to see, that's designed to actually turn off the microphone. And it's supposed to be a hardware circuit. So what you can see, when you plug it in, it does a boot sequence that takes a little while. But right away, that kill button is active. So you can see it, at least the light. Right? So this suggests maybe it is done in hardware. So what I want to explore is if we tear this thing apart, what actually happens when we go to figure out if it's actually being done in hardware or not. And if we reverse engineer some of it, I think we can do that. So luckily, we have the full Echo Dot here, but from the previous video, I actually ended up with, I don't want it to make noise. I ended up with a few different PCBs, so we can use these to make our kind of reverse engineering a little easier because I don't have to take it all apart, as you saw in the other video. So I'm going to start with so this is the top part of the board. And so if we take this off, what you can actually see is the top board here just has that one MediaTek chip. So if we take this plastic stuff off the board, you end up with this looking thing. And kind of what can we say about this guy here? Well, there's a few things. The first thing is that we want to identify the microphone. So there's a microphone here. It's these little packages. You can actually see basically they go through the board. So there's some holes here. This gasket's kind of stuck on, so I'm not going to pull it off. Here, 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 here. So there's actually 4 microphones around the board. So I think, they're trying to do some potentially pretty good audio processing. So you have these 4 microphones hanging out around the board. So one of the first things we might want to do is actually identify what these microphones are. So let's just flip that around. If we look at a microphone, this is what they look like. There's this S2390. So nothing too obvious, no like manufacturer that's obvious to me, but we do see right away, and we're going to see how this plays in a moment here. You've got, where's my pointer? Here we go. We have clearly 2 lines going off it, so some sort of signal out here. And this looks like power. Typically you'd have a big capacitor, and this might be like a ferrite bead inductor to provide power to this thing. So normally what you'd try to do is if we just Google, let's see here. So that S2390 microphone, maybe. And you can see if you get anything like that. This would be like a MEMS microphone, realistically. So there's some photos that look similar, but not exact. So, this is the kind of idea, right, where there's a hole underneath the microphone. So let's see, I think there's like if we look back, S2390, maybe an O afterwards. There's that M2 in the bottom. So unfortunately, it can be kind of hard to figure out some of this stuff. I have seen one before, so I've actually seen this looking part before, and I'm pretty sure what it is something like this. So you'll notice this looks, so just get the screen up here, sorry. I thought it switched on me. What we have here is, this is an Adafruit breakout board for a MEMS microphone. So I just had happened to find this before. And this looks very similar to the one that's on the board. Interestingly, so if we get the data sheet for this actual part, so again, this looks very similar to what was on the board. So this is probably the microphone. So what we want to check is what the possible markings are on the top here. And let's see, marking details. So there's an S if it's production, which is what ours start with. The rest of it's just a unique job ID number. So it's not even a part number. So this number on top that I was Googling actually is going to vary. So we can be pretty confident that our microphone is this part number right here. So I'm just going to make a note of, keep some notes here. Mic, SPH 0645, and this is a bit of a guess. LM4HB. So it's a guess, but we can be pretty confident on that. So going back to the board, what we have is that mic actually goes up. So where's my pointer here? Here we go. So this microphone here, the power for it actually goes to this transistor, it looks like. So they call it Q1. And this is to be honest, this is a pretty good sign, because what this would suggest is that the microphone power itself is actually turned off to turn on and off the audio. What I was concerned about is that it's just done in software, that it just doesn't read the signal, but this seems to be like a hardware power to the mic is turned on and off. So what we can do is I kept one of these boards here half alive, so we could actually just measure that rather than trying to guess. What we could see is, so we have that ability to turn on and off. And let's see if you can see the meter here. If we take our probe, and all I'm going to do is try to press that mute button while probing the power line that I was just showing you. So luckily there's a big ground pad, and I'm just going to look at the output of that transistor here. Okay. So as I press the button, you can see it actually toggling the power between 3.3 volts and ground. So that's a good start. This seems to mean that indeed they did actually switch the power on and off. So, these things are doing some sort of real hardware switch. Where's that signal come from is really the second question. Because if the signal's generated, right, if it's coming from the microcontroller, if it's just coming over this cable here, then obviously someone who has control of it could maybe switch it. At least there's an LED indicating the status. But what we'd like to see is this is done in some sort of discrete logic, in whatever some of these other chips are that aren't clearly the main microcontroller. So let's reverse engineer this a little bit further and figure out how they might have done that. So if we go back to here, where's the microphone? There we go. What we're going to start with is we're going to start with Q1 being the power on and off. And this is almost certainly done as a PMOS transistor here. Let me get a better pointer. So if we had a PMOS transistor, what that means is that there's going to be a gate, and if the gate is taken negative, the transistor gets turned on. So what we can guess here is that, where'd this go? What we can guess here is that the gate is probably this little one here. So if you were designing this, you'd have power coming in. This is presumably a 0 ohm resistor going to here, and then this gets switched over by the gate. So what our schematic looks like is, if we just kind of draw a a little bit. So this is probably going to get messy because I don't know where it's going to go, but let's say this is our mic and it's some digital output, right? So I'm not using the normal signal, I2S output, which is like, so I2S is a pretty common audio. It's a very fast signal. It's not I2C, and it has power. It's going along to a, let's try it the other way actually. It's going along to some sort of PMOS transistor, like that. And we have, it looked like there was a resistor between the VN and the gate. So what this means is that, you know, normally this differential voltage here is 0 volts, so this is off. To turn this on, we basically, so say this is, actually we know VN is plus 3.3 now. So to turn this on, we have to pull that to ground. If this is at 0 volts here, right, then now this is at like minus 3.3 volts, which turns on the PMOS transistor and you turn on your microphones. So now the question is, where does this signal come from? So that's the next step in this whole process, is going through, you know, the rest of the board to figure out where this thing actually comes from. So, you know, I'm just going to go through a whole reverse engineering. This is going to be pretty sort of standard stuff, but it might be interesting to see, you know, if you wanted to figure out yourself how this type of device was working, what would you do? So what I'm going to do is just sort of scan around the board from, where's our microphone? This microphone here. What we had is, let's get a better view. There we go. We assumed that there's a gate signal. So what you're going to see is this gate is going to be driven from some digital logic. So if I put one probe on the gate, and we could check this IC here. So I just have a continuity mode. So I expect it to be driven from nearby. What we don't want to see is it's driven from like either this IC here or this connector. So we don't have connection to that. That's good initial step. There's some other discrete looking stuff out here. Let's see, where is this coming from? Unless I missed something. There's a bunch of stuff out here too. So all I'm doing is kind of probing different locations. If you want to get a little faster, so one thing you can do is get a little wire brush. I think all of these black squares are actually the microphone, or some of them are the microphone stuff, so I don't want to necessarily probe that, but I'll just try everything. There's another discrete IC out here. And if we don't find this, what I might do is go from the other side, which is take a look at where the, oops, that was just me touching it. Take a look at where the switch is running, because that might also show us where it's coming from. So I'm not positive where this is driving, to be honest. Let's see. Unless there's some stuff over here. The issue is because it's just a continuity. If someone has like a 1K resistor or something in the way, I'm not going to actually get a beep. Which is why I'm not too worried, because that wouldn't be uncommon to do something like that. And I'm just not, I'm not going to probe every little resistor necessarily initially. So let's go the other way. Let's figure out where the switch is. So we have on this side of the board here, this is the switch. There's these two big LEDs beside it that is actually used to switch the thing. So if I again probe there, And one side of the switch is going to be like a positive or ground. And one side's going to be the side we're interested in. So I have something here that's like the middle of this resistor here. So let's take a look under the microscope to get a better feel for what that is. Okay. So where this was, where were we? Okay, so I think this is more the area. There was some resistors. There we go to the side. Okay, there we go. So where I was getting a ping off was right here. So there's two resistors, one just empty pad. So it was this middle pads going to the switch. And that was one side of the switch. The other side, we can check if it's ground or something like that. So normally we'd have that. Okay, yeah. So one side is ground and one side is going to those resistors. So we're just going to guess actually there that, if you were designing this, what would make sense is that what would make sense is that one side is going to be positive of these resistors. So we're just going to see if we see an obvious, sorry, it's kind of hard to probe under here. If we see some sort of really obvious like connection to a positive. So I'm not too sure. Let's try this. Let's try this side first. Okay, there you go. So you get continuity there. So this just looked like a positive. So assuming this is like a standard, some sort of IC where you have a ground on this pin, VCC on this pin, which I'm guessing based on just the thick trace and the decoupling capacitor, it routes to here. So we have some sort of pull-up resistor, and we can measure the value of that just to get an idea. So this should be some largish value if I'm right. So it looks like it's about 10K. Yeah, so that's about 10K. And we're doing this in circuit, so there could be influences, and that's 4.7K. And this side, whatever this is, let's see if it goes somewhere around here. Doesn't seem to, so we can figure that out later. So it might be that that's your output. I'm not really sure yet. So let's just update our drawing. I should have made this a little bigger probably. Anyway, so here's the button. Let's make it this way. So this is on off. One side is going to ground. One side has a 10K pull up. And one side has a 4.7K unknown. And so what you'd see here, right, is that obviously this is normally going to be just sitting at 3.3 volts. And then you could short that. And then, so you could measure it here. This signal itself would also be a valid point to measure. So we should try to figure out if these points go somewhere else on the PCB, because that's going to tell us where, where the interesting stuff is. So let's get this up. Okay, there we go. So where were we? Okay. This little zone here. So what we'd like to know is if this goes anywhere, or if this goes anywhere. So both of these would be kind of valid useful things, right, that are going to tell us something about what the device is doing. So let's check the output one first, or what I think is the output. Oops. No, there's just a little beep. Oh, okay. So we got a hit. Oops, sorry, I'm off the screen here. This is a really half-assed video. So there's a hit on some capacitor over here. And for the output, that 4.7K output, it looked like. Let's see, did I get that again? Or was I wrong? This one over here. Okay. So we can go forward. Let's keep going on this adventure. So what I was beeping on is right by U15 here. So there's this huge capacitor, right? Like this is massive. Like look at the size of the other one. So this must be a pretty big value. It's going into this device here, which the other inputs are presumably this is just like a power, ground, and then like an output. So we can try to look up this UP9, figure out if we can find that's anything. We're expecting this to be some sort of trigger or something like that, maybe. But let's add this on to our schematic. So we have a big ceramic capacitor. I'm just going to write big. Right, so what this looks like is this looks like maybe like debouncing using an analog. And it's going to be quite a slow time constant, but that's fine for, human interaction. And this is U15. VCC. And with U15, it says UP9. Just give you a UP9CB, I'm going to guess. UP9CB. So I don't know, these codes can be a little tricky to figure out. So they doesn't always work. And it looks like, this package, I don't have calipers here, but I'm going to guess that this package is like SOT 23.5 or... So this is like SOT 23.5. There's a few packages that are similar. So, now we have this. Oops. This here. SOT 23.5. 232 or 3.5. There's a few others. I forget exactly that are like that. So if we search, let's just try this now. SOT, UP9, SOT 23.5, says missing, UP9, that doesn't seem good. What is this though? A switch? So the other thing I'm trying to see is, is there something that the pinout matches? There's no UP9. So that doesn't really make sense. Regulators. So it could be like a Schmidt trigger, which are pretty commonly used. Pretty commonly used if you like have that slow changing analog signal. It could be like a buffer or inverter or something like that. Oops, inverter. Okay, nothing too much. So this one's not really critical because I have a feeling that we can get away with ignoring, knowing that it's one input, one output. Interestingly, there's kind of a diode in the output, which is a bit weird. But let's see where this guy goes. So let's just keep going with the reverse engineering stuff. So what we're going to look at is we're going to say we know this is here, and we'd like to know where this pin goes. Okay, so it seems like it goes to middle pin here. Oh, and it goes to 2 spots on this guy. 1, 2, 3. Nope. Yeah, pin 3 and 4 pins up from the other side. So the next question is, what is this I see here? So we got to go back to our microscope, and you can see it says LX744932. And where the output was going was this pin here, and then 4 pins up as well. So let's actually, before I pull up that, let's go back to our powered up device and take a look at what's actually happening with that pin. So right, we have that unknown part yet right now. So what I don't know is, so right now the microphone's on because the thing's not red, that would be off. So all I'm going to do is, if you measure the voltage at the output of U15, right, the question is, what is this voltage? So it seems to be 0. And, oh, our microphone's off now. Let's see. So this was in the switch path, remember? So we expect this to just be affected by the switch. So if I hold the switch button down, it goes to 3. If I release the switch, it goes to 0. So this looks actually just like an inverter, because the input to it's the opposite, right? The input's normally at 3 and gets pulled down. So that whole Schmidt trigger guess makes sense if we consider that. So probably what we have now is that we have this unknown U15 that's actually serving as a inverter to feed the signal into this digital chip here. So now the question is, what is that digital chip? Okay, so if we look up the marking on that chip, so we had that LCX74, and this is actually an old school flip-flop. LCX74. So all this has is it's 2 D-type flip-flops. So this is a pretty classic part, you know. So this is actually kind of a good sign because, you know, again, we're looking for stuff being done with discrete logic. So what I'm going to do is I'm going to copy this schematic because things are getting a little crazier, and I'm actually just going to dump it on a photo I took here. Grainy photo, but it doesn't really matter, of the board. So now we can sort of make our life a little easier. Let's make a layer. Come on. And I think pin 1 is this way. Oh, crap. Okay, yeah, so this is the right direction. And all we're going to do is kind of vaguely shrink this. So that it all matches up. And this will just make it a little bit easier, you know, as we're playing with this thing. Because what I'd like to do is, again, get back to the point that I have it sort of reverse engineered. Okay, there we go. So, and we can adjust the layer opacity to make this a little easier to deal with. Okay, so what we had, if you remember from me beeping it out here, was that the button, and let's make a new layer, that's my notes. So we had a input here, where I'm just going to beep it out on this other board now because I already forgot. 1, 2, 3, 4. 1, 2. Okay, so it's 3 from the top. So it's this clear pin here, CP1. So that's the asynchronous clear is actually routed right here. And it's also going to 4 from the top, so this clear pin 2. So there's 2 D flip-flops. Both of them are connected to that same point. What that seems to mean is that, the output, when you press the button, whatever it's doing this asynchronous clear on the flip-flops, which is interesting because as you press the button, it toggles, right? The button's not just an always off. So there must be some interconnection between the two of these, I'm going to bet. And CP. Oh, or is CP the clock? Sorry, did I lie to you? Would I lie to you? I bet you it is. Oh, no. CD is the clock, sorry. I'm pretty sure. Let's see. CP or CD? These names there. Oh, clock. Okay, so now that makes actually a lot more sense. If it was a direct clear, okay, so the direct clear are active low. Okay. So we have a D flip-flop with a clock, and I'm going to add this to my little schematic down here. Let's see if this works. This guy. Okay, so this is an inverter. We now know Schmidt trigger input, we're going to assume. Oops. Okay. There we go. And what we have is 2 D flip-flops. So we have D1, CP1. So a D flip-flop, if you kind of remember, right, all that does is this is your data store flip-flop effectively. So really it's just propagating the input on D to the output Q, and then there's an inverted output every time the clock pulse goes high. So there's got to be some interconnection. What I'm going to guess is that they're actually interconnecting Q2, the input. The inverted output goes to the other one, or something like that, or back to itself. Like there's got to be some way that they're doing the changing pulse type. So we also have a asynchronous set and asynchronous clear. So if these are directly driving the mic stuff, this is SD1. We have set and clear at the bottom. Okay. So one of the first things to check is what are these set and clears going to? What I'm afraid of is if the set or clear routes to, the microcontroller, it would be a way to override the button press. So I'm hoping that there's no way to override the button press, so you always have control of the device. But let's take a look. So if we go to our thing here, what you can see is I can first check the clear 1. So I'm just going to check pin 1 is one of the clears. And it's routed. Looks like it's routed to clear 2. So let's get you a better view as I probe, maybe, if I can. So all I'm trying to do here is probe with the data sheet up, this is the clear for the first one, and it routes to the clear for the second one. Let's see if it routes anywhere else. So they're connected together, and check here, here, and I'm going to check the connector off screen. Okay, so nothing there. Interesting. Nothing up here. I'm just going to scan some other spots on the board. So if you want to look around here, all I'm doing is scanning, you know, some of these other chips here. See if we can find that. I'm kind of assuming that, no, that was the same thing. It's routed somewhere here. It wouldn't just be floating. It's definitely not just floating. What I had actually expected was that maybe it was just pulled to VCC, like if they're not using it. Just make sure. Ah, okay. So I tricked myself by only checking the one. So it's actually connected to the second data input. So if we look here, it also connects to there. So this is the second data input, connects to, does that make sense? CD2, yeah, and CD1. So what we're gonna do is, if I show you, let's just look a little more detail here. So we have CD1, and this connects up, oops, I can't use that, to CD2 and also to D2, which also means that that seems to be, and this, again, this doesn't yet make sense, because D2 is another input, right? So these are all inputs. So there's got to be, there's something missing here. Maybe we go back to the overhead view. Let's see, maybe I missed another pin on this side that it's connected to. Wait, was that just a little one? Yeah. Maybe that's a... No, that actually doesn't seem like there's a connection there. So one of the things is it's a bit tricky. You're trying not to block it. Okay, so there's no connection, so we get rid of the D2 connection. I guess that kind of, I mean, it makes more sense that way, but there's still an unknown. So there could be a pull-up or something. I don't think there's anything really on the other side of the board. So there's definitely a missing connection there somewhere. So that's TBD. But let's go back to this and let's erase my incorrect connection. So the next thing is, let's see the rest of this guy. D1, SD1 would all be interesting. So these would be more inputs. So what we're gonna do is we're gonna look at, let's look at SD1. I mean, again, these sets and clears I'm curious about. So if I go 4 up, so we can actually see this one on the PCB. Looks like it's routed 1, 2, 3, 4. Okay. Just looks like it's routed up here, which I suspect. Oh no. So it's routed to some. You can see there's a bunch of stuff going on here. And it looks like maybe there's a pull-up on it. So it seems to be going to here. 1, 2, 3. This would be the set. So the sets are both connected together as well. So why don't we go back to this. And just rather than draw it back on that. So we know the clears are connected together. And those ones go somewhere we don't know. We know this, oh, go away. We know the sets are connected together. And what it looks like is, let's get a camera view up here. Is the sets go to this TM1. And this looks like possibly power, but no. So you can see there's a sort of an interesting setup here. Okay, so remember this was power actually, because this is what powers the microphone. So this looks like we've got some sort of pull-up on them. And I'll bet you this is where the clears go. Let's see if that solves that mystery. So if we beep this out on our other board, what you want is you want the flip-flop here, and what I'm going to claim is that okay, perfect. So now we know where the clears go. So they seem to go nowhere except for a pull-up resistor. So I'm not sure why it's not just directly connected. They might be afraid of glitches actually, because it's discrete logic, right? If you get glitches, that can happen. And you have 100K. Okay, so this is actually a time delay here. So you have 100K pull-up with a fairly big capacitor. So I suspect this is just related to some startup stuff. And the other ones, let's see, pull up on this side. So it's a much smaller capacitor. So it's 2.2K. And it seems like it actually goes somewhere else. So the sets, which one was that? The sets go somewhere else. Yeah. But the clears have a sort of nice pull-up. So let's get rid of my mystery thing here. And remember, these are active low. So if we have a pull-up, that's disabling them. So the clears have a 100K resistor with what looks like a largest capacitor. So that is the clear, and then the sets have a 2.2K pull up with a smaller capacitor like that. So again, probably some sort of glitch filter or something like that. But this does go somewhere else. We do see a via here. So where does this go, and actually what does that let you do is maybe one of the questions. So let's see if we can't figure out where this guy goes, because that's kind of an interesting, right, this via right here. So this actually, this TM1 is going somewhere. And again, what we don't really want to see, although it would make it interesting, is if this TM1 goes to this chip here or this connector. Ooh. Okay, so goes, let's pull this over. Now the question is, this might just be able to turn it off, and we can test this really easily. So it actually routes to your, oops, you just are out of screen, sorry. Boom. So this TM1 actually routes to this connector here, which is going to the main board. So this TM1 is your flip-flop set. Now we don't, how does the rest of the circuitry work? I don't know. So we don't have to worry about that though, because we have my little test board here. And all we need, is we can measure some of these voltages. And what you can see, so this is regularly at, let's get you up on this view here, regularly at 3.3 volts. So that's the TM1. And what we want to do is we want to take TM1 and we actually want to short it out. So when I short TM1 out, the question is, let's see if we've got some wire around here. What happens to the microphone circuitry? We have this mic that can go on and off. So let's try shorting out TM1 to the ground and see what happens. Okay, so it turns the mic off. And if I touch it again, nothing happens. So if the mic was off, nothing happens. And if the mic was on, it goes off. Okay, that's cool. So what this proves is that this TM1 does route to the connector. Yes, that seems bad, but it only lets you turn the microphone off. So that's actually pretty cool. So far that's a good sign, because the only connection I can see is an ability to mute the microphone from the main processor. So they have a way to mute it, but not a way, hopefully, to unmute it. And again, if I look at the other one, so the one that's risky is the clear. Where is this? Over here. And this one, so I'm just looking at the clear pin. Doesn't do anything. So it seems like you can find a way to mute it, but not unmute it. Okay, well, let's finish off. Just kind of, I haven't actually seen how these outputs route anywhere. So I'm not going to maybe do a full reverse engineer, because really it's these inputs are the biggest concern, right? If there had been a way to drive those inputs from the micro, this would have been really bad. But we can check, for example, D1 or anything like that. So D1 is pin 2 as well as pin 12. So if we look at pin 2, where does that go? Okay. 3 from the top. So it looks like D2 and D1 route together, which is okay. Where do they go, though? Because, that has to come from somewhere. That's the part that doesn't make sense. If I didn't screw this up again, let me just make sure. Yeah. I would have expected some of these outputs to connect together. Unless it's some of these resistors over here routing stuff. Over there. So there must be some other funkiness going on with this board. Because what I don't seem to see is where the input to the flip-flop goes, unless they're just... No, they're not just strapped to... Where's this? No, this is just pin 3 from the top again, which is D2. So it might need some more investigation, but what it seems like, right, is D1 also routes to D2. Which, you know, there's got to be some connection to the rest of this for any of this to make sense. So let's take a look. Let's just get another board. It's a bit easier to play with here. Okay, so there we go. Oh, nope. Just a ground. Oh, wait a minute. So there's these little beeps, but they're... Oh. Okay, there we go. So what is that? Let's take a look under the real microscope. So where we had a hit was somewhere up in here, it seemed. Let's just check that again. Where was it? Oh, interesting. Wait, oops. That was the wrong one. This is the D1, unless I was just shorting. Oh, there we go. Okay, so D1 is going to the output. So D1 and D2 go to, this is the actual VCC that's going to the device. So that's kind of cool. So there's some pretty serious feedback going on in terms of they're actually checking the voltage going to the microphone. So let's take a look here. What you have is, where's our microphone circuit? Up here, right? This plus V to the microphone is actually D1 and D2. So what happens here is when you press the button, right, it's forwarding this microphone voltage. So if the microphone was on, if this was 1, for example, 1's going to go here, and if the microphone was off, a 0 is going to go here. So to be honest, that's not quite what how I anticipated them doing it, but this is interesting because it's actually going to be using the voltage on the microphone as part of the feedback. So there's got to be a little more in here, and a little more in how we drive this connection up here. So that's kind of an interesting schematic choice. So let's push this. You know, I said I wasn't going to do any more, but it's kind of brought up some interesting stuff. Let's just see quickly where this goes to. So what we're curious about now is basically Q1. So some of these outputs have got to go somewhere, right? So if I have the my other screen here, all I have up is this right? And we already figured out that D1 is going to here. So Q1 and Q1 not, pin 5 and 6 would probably be something we want to check out. So I think I've got that up here. 1, 2, 3, 4, 5. It's got to be something somewhere. Maybe it's the inverted they use. Okay. So I got a hit up on the other side of the board for the inverted output. And it looks like there's 2 hits, so it's this and this. So if we go under the real microphone, microscope, microphone, let's just get that up. Let's try. Okay. Where I was getting a hit, I think, was around this part here. So it looks like ground VCC. What is the part number on this thing? Okay, COOR. And that looks like an 8 TSOP maybe. So what we're gonna do is let's just search that. See, and I think it was COOR. I don't think it's like, I think it might be 00, not like Coors Light. Okay, yeah, look at that first hit. Logic gates. Oops. Okay, so that's even easier. It looks like this is directly part of a datasheet number. And it'll be a NAND gate, so that kind of makes sense, right? If we needed... Let's see if we can find our package in here. Top side markings. No, see, this isn't right. MS00. Because that's not the right package or anything. So let's put TSOP. So this seems to suggest, I don't know if this is going to be a bunch of spam, this website. So this is the same. So a bunch of stuff's coming up, 2-input NAND gate. Let's just try this. So you can see I didn't really do much of this ahead of time, otherwise the video would be a lot smoother. But let's just check. So they were always going to have this package marking information. There we go. Perfect. Okay, so C00R. Okay. Visa. Okay, I had it not quite right. So you always got to be careful. There's so many variants of these package types. But this is what we want here. So we can see the package name. It doesn't really matter which we take. So the top are inputs here, and on this side, these 2 are inputs. So all we're going to do is do our same little trick on layer 1. Let's go find that part. And you know, as I mentioned, I took the wrong package, but I don't really care. Oops, are we on layer 2? No, we can't be, because layer 2, that should be paste it onto this layer. Layer 3. Okay, whatever. Now this one might actually be so small that I'm not really sure. So it's this orientation. Yeah, this is going to get tiny, but you get the idea, right? And we actually see, so what's sort of interesting is that there's like 2 resistors on each. Oops, what did I do there? Did a bunch of skew stuff. There's 2 resistors on each input, so we can actually kind of see the design pretty easily. And where I was probing was the other side of these resistors here. So what I was actually probing, okay, thank you. Adobe, we don't need this. Was, let's get back to this guy, right here. I believe where was it here? Okay. So there's 2 NAND gates, and let's see if this other input goes to the flip-flop. Oh, it does. Okay, and the other input is going to so this is 1 Q naught. So there's like a, oh come on. Oh come on. There we go. So we had 2 things. So we had a Q naught input here, and I just, what was it, layer 2 I was drawing on? I think. There we go. So this was like a Q1 naught. Should probably have a better tool. And this one is actually routed down here to Q2 naught. Okay, so we had Q1 naught and Q2 naught. Interesting. So I'm still not positive what the overall point is. And this side, so what happened here? We actually had a little more going on. I believe, let's see, so one of them, Q1 naught routed to the other NAND gate as well. Let's see if Q2 naught also routes there. Yeah, it does. Interesting. So, again, we have this like parallel construction once more. So one of these also goes to Q1 naught, and one of these also goes to Q2 naught. I kind of drawn over the rest of this, but let's see. So if we go back to our design, so this is Q1, Q2 naught. We have some NAND gates here, and Q2 naught or Q1 naught goes to both, and Q2 naught goes to both. So interestingly, there's kind of like a weird, I don't know if they're doing this to claim backup or something like that. But okay, so look at this, right? You have like D1 going in here, and it's the same input going to both. You have the same clock pulse going to both. You have the same set and the same clear that seem to be going to both. Both outputs are then used together with a NAND, 2 NAND gates, right, where the inputs are coming from the opposite side. So it's almost like they're using this for a like to claim that there's a dual circuit, which is kind of weird because, I mean, these little logic gates wouldn't ever, you know, they'd never be defective or anything that I can imagine. So it's sort of weird. Yeah, I'm not totally sure. And, because this is a NAND gate, what you're going to get is that it's almost being used as an inverter, right? Because if these are both high here, which should be the case because they're mirroring each other, then this is going to be low. And if these are both low here, then this is going to be high. And if one of them is low and one of them is high, so if there's some error, then this is going to be high as well. So maybe that's the whole point, is that somehow it's being used just to confirm that if there's an error in one of them, the microphone is always disabled. I'm not really sure, but it's sort of an interesting design. So, or these both go in a different spot. It could be there's a separate point to it. So let's take a look at the rest of this. What I'm expecting now is, where does this output? There's two outputs now that should be the same. So let's see where that's going. Let's just look here. If this is one of the outputs, make sure I don't have a short in my connection. Where's that going? Could go over here somewhere. I mean, this is, remember, all of the circuitry is out here. Okay. So where I'm getting a hit is actually this output all the way over here, and I don't think that's a short. No, it is. It's just the VCC. I need to do a better job isolating. The thing is, these are so small, and I don't want to get too close. Okay. So I think now I just have that output. So there's something going on around there, but it's not connected. Oh, my meter turned off. It's terrible timing. Okay, something around here. It's not connected. So this, we're closing the loop now. This is the input to. Yeah. Okay. Now close that loop. So this is the input. One of these anyway is routing to an input. So if we go all the way back here, we can take this guy all the way around. This isn't a question mark anymore. This goes over to here. There we go. So at least one of these outputs is going to the MOSFET, right? So now it's effectively, it's interesting because there's almost like multiple inversion steps here, right? So this is inverting it here. So we have the inverted output. It gets inverted here. This effectively becomes Q2. But then remember, this PMOS is inverting it again. So this is basically back to Q2 inverted, which is then fed back into the flip-flop. But rather than, so what I expected, to be honest, is, I'd be lazy and just route Q2 to this input D2. But they're in fact using the whole chain to validate that everything's working as planned. So it seems like there's quite a bit that's gone into making sure that this whole chain is working. So a final question is, where does this last NAND gate output go to? So one thing I haven't figured out yet, there's also an LED, which I'm less worried about. But I bet you maybe this last NAND is somewhere over here. Driving an LED or something like that. Just hard not to have my probes in the way of each other. Okay, so there's no more connection to there. It could just be a monitor pin too, actually. Right. So I wouldn't be surprised if there's some other connection to let you monitor. Oh, okay, there we go. So there's some thing over here that if I didn't screw up and just short the ground, nope. So it's going over to this U6 part. Let's take a look at what U6 might be. So it's routed somewhere over here. And well, the one thing we, as I mentioned, we totally have ignored. So let's just take a look again. So maybe this is like an input. Where's this guy go? Or is this more with the microphone? Maybe there's another enable pin here. So we have some other stuff. There's this big resistor. Let's just take a look. So on the back side of this guy, what we have is these big LEDs here. So we can actually, one half of that is going to go to just positive somewhere. But let's see. If there's any connections around. Because this is kind of in the area. Maybe this is the wrong side. I'm just guessing which side is which still. So we should still see. Worst case, you know what? Maybe I'll just power it up. But I was expecting to see pretty obvious. Okay, there we go. Maybe TM5. So one side of the LED is going to this test point there, which could just be the constant voltage side, and doesn't seem to be anywhere over there. So let's just power it up and see what I suspect. Because the other thing is, right, it could be that there's a monitor pin, like for the microphone, that's also killing it. So maybe one of the reasons it does double duty is, let's just scope some of this, or not scope, but do some power measurements. So there you go. So here's my board. And what we're a bit curious about is a few things. So the U6 is over here. I'm going to put my finger on this kill button. Oh, sorry, the meter's just off screen for you, but you can still see a bit. So there's an input. One of the inputs to this U6 is definitely following, which is what you expect. And are any of the other pins doing anything? Doesn't really seem like it. So I'm just toggling. Oh. Okay, so one of them goes between like 0.8. So maybe that's just like an LED driver or something. Just seeing if there's anything more obvious. Okay, so it seems to be switching this this other pin between 0.8 volts and off. It's not entirely clear then. Yeah. So what we're seeing, if I grab this one here, is that, so there's U6 here is what I've been probing. And the on-off signal is routed to here as well. I don't know if we'll be able to figure out what that is. It's going to be a difficult one with just the small codes. VM, yeah, I'm not even going to bother. And it seems like there's a signal here that's being switched between 0.8 volts and 0 volts. So assuming that's really the case, right? What we have, and I don't know, this seems to route to one of the, what's this chip? Is this one of the microphone receivers? So there's definitely some other switching going on, but the important thing that I really wanted to get through, right, was figuring out who drives this signal. So the microphone power signal is used to physically switch the power to the Amazon Echo Dot microphones on and off. So it's kind of cool because you can see, you know, they've done a fair amount of effort, it seems like, to actually get on these boards the microphone switched off, as well as having like sort of a guaranteed way of doing it. And it's cool too because you can see in this schematic here, right, that to even deal with the fact that you need a way, so this pin here comes from the microprocessor control, but that only lets you turn them off. So this is only a disable only, as far as I can tell. So there's no way even really to enable the microphones from the microcontroller or from, you know, the Linux system. So what's important there is, right, if someone had control of the Echo Dot or even Amazon itself was forced to, it seems like all they can do is disable the microphone, turn on mute mode, and not disable mute mode if you've turned it on. So, you know, maybe there's something I missed in the reverse engineering. This was just me going through some interesting stuff, but it's kind of to give you an idea what's involved in taking these devices, taking them apart, and trying to figure out, you know, how does the privacy guard that they claim they have there, how well does that work in real life? So thanks for watching. You know, it's another kind of long-winded, unedited one, but hopefully you kind of saw some of the process and found it interesting.